All right, so today I'm going to talk about Elixir and specifically concurrency in Elixir. But in talking about Elixir, I have to talk a whole lot about Erlang, and I'm going to do that. But I'm also going to talk about processes and threads and how concurrency works in other languages. And this talk is based on a talk I saw at Abstractions by Andre Henry, and he talked about processes, threads, and the death of Moore's law. And as I learned more about this, I ended up basing a lot of this talk off of Joe Armstrong's talk, Erlang, Software for a Concurrent World. So, disclaimer, I'm not an expert in concurrency, but I am an expert in Googling things, and so you can trust me to a high degree of doubt. So yeah. What is going on here? Okay, so first we have to define concurrency. So concurrency is when two or more tasks can start, run, and complete in overlapping time periods. And concurrency is becoming more and more important as we build applications because no longer can we just, we can keep throwing more servers at the problem, but we're kind of hitting Moore's law, where it's no longer are the number of semiconductors and transistors doubling every year. So we're reaching our limits in that regard, and now we have to look to concurrency to solve our problems. And think of like long requests or WebSockets. Those are problems that just throwing more hardware at the problem isn't necessarily going to solve in a single-threaded environment. You have to concurrently handle WebSocket connections because they're running for a very long time. So traditionally, when you had short request life cycles, this wasn't as important as it is today. But this is real-time is becoming the standard. So now that we know what concurrency is, I'm going to talk about different strategies for concurrent applications. And then eventually, I will show some code examples in Elixir and show you how it can be done. One strategy for concurrency is operating system processes. And operating system processes are great because you start it, and then you start another one, and they run totally separate, and they're isolated, and they don't share anything. And if Vim crashes, it doesn't crash Chrome. Everything runs as you would expect it to. And if you start typing in Vim, you don't see the text you typed in Vim show up in your Chrome address bar. Like that doesn't happen because they're separate, and they have separate sections of memory, and so they can't even touch each other. And if Vim does want to talk to Chrome for some reason, it has to send a message to Chrome. So that's where message processing or message passing comes in. Unfortunately, though, processes are expensive. Like operating system processes take up a good bit of memory. So say you boot your app, and then in another process you boot your app. Well, now you have two instances of your app running, and is that necessary? So they use a lot of memory. And then you have OS threads. So operating system threads are lighter than processes. They don't block each other, and they run on separate CPUs, so they are truly parallel. Unfortunately, the problem with threads is that they're still pretty heavyweight. And I'll talk about how heavyweight, but they have shared memory, which is not good. So I'm not the person who coined this expression, but shared mutable state is the root of all evil. And if you're using threads and you have mutability in your language, then you can overwrite data, you can corrupt data, because everything is happening at the same time. So, things can get kind of crazy with threads. And then you have green threads. So OS threads are a construct provided by your operating system. But green threads are something that's provided by your language or your runtime. So prior to Ruby 1.9, Ruby had green threads. And green threads are great because you can spin off 1,000,000 green threads and it's fine, because green threads aren't actual threads. They're created by the the virtual machine rather than the OS, and you don't have to allocate a stack for that amount of memory. You can just run the code you need to in a separate green thread. Problem is they're not actually concurrent because they don't run on multiple processors. And so, well, they're not parallel because they can't run on multiple processors. And so a blocking I/O operation can block all green threads. It's not good. So how heavyweight is heavyweight? So a POSIX thread has a configurable stack size, but the default is 8 megabytes. And you can prove this on your own machine if you run ulimit-s. And you'll see it'll say 8 megabytes. But luckily for us, most threads aren't 8 megabytes because most of the languages we use know that that is an extremely large amount of memory to allocate. So the JVM, .NET, RubyVM, and CPython, they all use 1 megabyte by default, and most of them are configurable, like before you start your app using an environment flag or something like that. But 1 megabyte threads are still pretty large. So if you're doing some small computation, you probably don't need to allocate a whole megabyte, but you have to because you just have to. That's how it is. And this is a quote from Joe Armstrong that apparently was a little messed up. But he says that Erlang is a concurrent language, and by that I mean that threads are part of the programming language. They do not belong to the operating system. That's really what's wrong with programming languages like Java and C++. Its threads aren't in the programming language. Threads are something in the operating system, and they inherit all of the problems that they have in the operating system. One of the problems is granularity of the memory management system. The memory management in the operating system protects whole pages of memory. So the smallest size that a thread can be is the smallest size of a page, and that's actually too big. And so we kind of need a combination of these different approaches to concurrency. So we talked about OS threads, we talked about OS processes, we talked about green threads. And so a thread is too heavy, a green thread isn't actually parallel. So what if we were to combine the two? And that's what Go does. So Go it has the green threads, but then it multiplexes the work over multiple native threads. And so what you get is you have a dynamically allocated stack, which is good because you don't have to allocate 1 megabyte. You can allocate 2 kilobytes to start with, and then you allocate more as you need it, which is great. And then because they're green threads, you can spawn a whole bunch of them, and they'll be split. The work will be split and divided over multiple OS threads. So if you hit a blocking operation, you can continue your Go routine. So that's really good. But you still have the problem of shared mutable state. And so I want to talk a little bit about shared mutable state and why that's bad. So this is what shared mutable state looks like. That center red section is your shared mutable state. And let's say the circle on the left is process A, or thread A, and on the right that's thread B. So someone once said, I don't know who, a software developer introduces concurrency into an application, now 5 problems you have. And so you've probably heard a similar statement about regular expressions. And what they're talking about is this problem of shared mutable state. So normally we would deal with this like, oh, just put a lock around it. Like don't let 2 processes do that at the same time, and just like let one happen and then the next has to happen, or before the next can happen. And okay, cool, we solved that problem, let's move on. And then another problem comes along and we'll just put a lock around that too, and then that'll be okay, and then everything will be great. And so next thing you know, your concurrent system is not, you've taken away the possibility of ever being truly parallel by putting a lock in place. And so languages like Ruby or Python, they have a global interpreter lock. So Ruby can never truly be parallel because it has this global interpreter lock that even though Ruby has native threads, the language runtime prevents it from actually being parallel. And I'm sure they'd love to fix that, but. And then, the other problem with shared mutable state is fault tolerance. So say, thread A makes a little change, and then it, crashes for some reason before it got to finish what it was doing. Well, now you have corrupted state, and now process B is going to fail. Because the expectation that it had is no longer proving true. And also, where do you put this shared memory? Like, does this shared memory belong in thread A or thread B? Or where do you keep that? Do they both have it? I mean, where does it go? So then we get to Erlang. Woohoo! So Erlang was built for telephone systems, and telephone systems need to be able to handle multiple simultaneous phone calls. And they can't afford to fail, and they are highly concurrent, and they can't have any downtime. So, you can deploy to an Erlang process and without ever stopping the app, swap code out while it's running, which is incredible. And it's extremely concurrent. And it does that by not sharing any state because it has immutable data structures, and by sort of doing what Go does where it multiplexes over multiple threads, sort of. So it's not the best of two worlds like Go, it's the best of three worlds. So now you've combined green threads, native threads, and OS processes because an Erlang process is isolated from another Erlang process. So if one Erlang process fails, it fails, not everything else. Everything else stays running. And because Erlang threads or processes are so lightweight, you can spin up thousands of them, like millions of processes. So like I said, there's no side effects, not an OS process. It's managed by the VM, not the OS. You sidestep mutable state, and processes communicate through message passing, similarly to how I said that, if Vim had to talk to Chrome, it wouldn't just call a function. And it's fault tolerant. And as I said, Erlang's threads are extremely lightweight, and you can actually verify that. It is, on my machine at least, 340 kilobytes, or bytes, 340 bytes. And so before when I was talking about Go, I said it initially allocates 2 kilobytes, which is really small, but that's so small. And so, you might be wondering, like, why is that important at all? Like, I don't see the benefits, but WhatsApp does. And so they had 2 million concurrent WebSocket connections running on one server. And granted, this is like a pretty beefy server. They had 24 cores and 100 gigs of RAM, I believe. So pretty beefy machine, but they were able to handle 2 million concurrent connections. So think of 100 gigs of RAM is 100,000 megabytes. And if each thread that you spin up is 1 megabyte, then how many concurrent connections can you have? So wouldn't that be, I'm not a mathematician, but I think that would be 100,000. And so the fact that you can do 2 million is crazy. And I think there are a lot of other things that play into the equation that I just laid out for you, but I don't think you would ever get to 2 million in any other runtime. Well, not any other. Closure could probably.
Roku, baby.
And so now I want to talk a little bit about specifically Elixir. And so this is what message passing looks like. You have a PID, that's the little guy on the left, and he sends a message to a mailbox, and the guy on the right just checks his mailbox, and he's like, what do I got, what do I got, what do I got? And so, actually, here's the hard part. All right, so let's look at a process. Okay, so I have this module ping, right? And we're going to do a ping pong type of thing. We're going to make two processes talk to each other, but first we're going to talk to this process. So when I call ping.start, it's going to spawn a new process. If I were to say ping.handle ping, it would block. Like, and I can demonstrate that for you. And I wouldn't be able to do anything. Right? This is what blocking is. I can't do anything now. I'm blocked. Let's try that again. So I can say my ping PID equals ping.start. Right, so now I have a process running. And so ping PID is a process just like I'm currently in a process. So that's my PID. I can send a message to ping. So send ping PID. And if you look on the left here, ping is going to receive a count and a client PID. So I'm going to send it, let's say 1 for now, and I'm going to send it self. Okay, so I send a message, it logged ping 1, and now if I check, I received a message back. So see here where it says send client count self, that's what I just received, and calling flush shows me the message that I received. Okay, so that's cool, but let's do something even cooler. So this actually shows me all of the processes that are running right now within this application. And let's look at our message queue specifically. Okay, and I'm sorting by which process has the most messages in its queue. And I'm going to spawn up 100 messages. So let's say enum.map1 to 100 function x send ping PID x self. All right, so I just sent 100 messages to my queue. So handle ping, you can see right here, it has 99 messages in the queue. And it's going to grab those off and then restart the ping and wait for a message. Grab it off, wait for the ping. And I'm getting these back. It's logging as each one executes. So that's cool, I think. So actually, I can make two processes talk to each other. Let's start that again. Ping PID equals ping.start. Pong PID equals pong.start. And I can send, I'll send a message to ping PID. And I'm going to say, let's start with 1 as the count. And if you look at Pong, it's going to increment the count once it receives a message and send it back to whatever sent a message to it. And I'm going to give it the Pong PID this time, so it's going to send a message there instead. So we get ping pong, ping pong, ping pong. So these two processes are talking to each other, which is like minimally cool. So that's great. So I've shown how processes talk to each other, how you can talk to your processes. I want to talk to you about another thing that I think is really cool. So let's talk about distribution. So when you have concurrency, you now have a system that can easily be distributed. And Erlang gives you some really cool ways to do that. So let's say IEX sname foo at localhost. So I'm just giving a name to this, I don't know what to call it, process that I'm starting, OS process that I'm starting. Okay, and so imagine the terminal on the left is like a server a million miles from here. It doesn't really matter too much. So let's paste in some code here that I have prepared. Let's also maximize this. Can everybody see? Can you guys see?
That's good.
All right, so I'm going to define a module with a function called world. So over here I can say hello world. Cool, and it logs yo to the console. So now if I go over to bar, I can say hello.world, and what do you think is going to happen? It's going to get an error, obviously. That would be crazy if it didn't, though. However, I can make this over here talk to foo. So this is bar, that's foo. So I say node.spawnLink, I give it the name, and then I can call hello world. And boom, it logs over here. So we've just built a distributed process. And we can do the same thing with our ping pong process. So just imagine that ping pong isn't the same. Ping and pong aren't defined in the same file. For this example, it doesn't really matter. Okay. So over here, I'm going to say ping pid equals node.spawn link foo at localhost function ping.handle ping. And so remember, handle ping was that blocking thing that said receive, and it's going to receive a message, log, wait a second, and then it'll send a message back, and then it's going to look for messages again. So now I have this ping pid, and I can do exactly what I had done before with the pid. So I can send a message to it, right? So send ping pid one self. And this is the same code I had written before. It's just I got that PID by starting it in a different process or on a different node. And it works as I said it would, so of course it does. And I can do the same thing that I did with Pong. So Pong PID equals, and I'm running Pong over here in bar. I can send ping PID one Pong PID. And now they're communicating. And so these two processes could be communicating across the network, which is crazy. So when you have a concurrent system, you get a lot of benefits. It's really hard, but the goal of Erlang is to make it easier. And so you get a lot of things when you have a concurrent system. You get distribution, so you can distribute across multiple nodes. And part of fault tolerance is distribution, right? So if you distribute your app into multiple processes, and one of those processes crashes, then Erlang will know how to start it. But what if the server shuts down for some reason, or like everything goes to hell and like Amazon shuts their servers off? Well, if you have another server, then you're still fault tolerant. So at a certain point, to be truly fault tolerant, you need more than one machine. And so I think distribution is the way you achieve that.
If you kill the thing on the left, will the thing on the right die?
Good question. Where is my mouse? Anybody see it? There he is, yeah. Boom, no connection. Okay, so one final example that I want to show you. So let's look at a Phoenix app. And so the reason that didn't fail well is because there was no supervisor attached to that process. There was nothing to tell bar, oh, foo died, we got to restart that. Everything is going crazy. And so that's kind of the role of supervisors. Supervisors say, if this process dies, I know how to restart it. And think of your app you have apps, and you'll have multiple processes. So you'll have Sidekick, you'll have Rails server, you'll have different processes running on your machine, and you'll often have something like Upstart manage those processes and make sure that if they go down, they know how to come back up. So that's a language construct in Erlang, and by extension Elixir. So this is a Phoenix app. I just ran mix phoenix.new Phoenix app. And let's pull up that observer thing that I showed you earlier. All right, so we have this big list of processes, and that's cool. It shows us the message queue, which can be, Jose Valim was talking about when they were trying to demonstrate that Phoenix could handle 2 million concurrent connections, that initially they had some trouble and they didn't get there on the first try, obviously. But they looked at the message queue and they said, oh, this process is backed up, there's our blocker. And so that's really nice to be able to see in production, like, here is my blocker, which a lot of times is hard to tell. And so this is an application tree. And so this is your application, and then you have a supervisor watching your repo and your endpoint. Your endpoint is like your HTTP server, your repo is like your database connection. And our database connection, in this case, has a pool, and it's got multiple connections to the database and the pool. But because this is a supervised process, if we kill this process, it's going to come right back. So let's kill it. And now you can see we have this PID that is not next to these PIDs because it's a new PID. And so when the mentality behind Erlang is crash, let it crash, it's fine, it'll come back up, and just let it crash. It's better to let it crash than try and rescue these exceptions because it'll handle it. So that's all I got. Questions?
So if you look at the operating system processes now, and if you have more than one CPU, will they be distributed across
More than
CPUs?
yes. So Erlang has its own scheduler. So right now, I think I'm running. Let's do this. All right. So I'm running. I'll run IEX, right? Interactive Elixir, which is Erlang, behind the scenes, sort of. And actually, let me start it like this. Okay, so the PID should be, what is it? $! Right? Yeah. Okay, so I can say PSM $! And these are all, so this is the process, and then these are threads belonging to that process. So Erlang's SMP, so Erlang wasn't designed, it was designed to be a concurrent language, but it wasn't designed for multi-threading because they didn't have that in 1986. But then if you read about it, it wasn't that difficult for them to add it, and they didn't have to majorly change the language because it was designed to be a concurrent language. So when they added threading, they just said, okay, so rather than having a thread run a scheduler, we'll have a bunch of threads run schedulers, and there we go. And so that's what you can see here. You have a bunch of threads, and these can all schedule work on different threads, or something like that. I only have half of knowing what I'm talking about here.
But it's just one core, if you have two CPUs.
No, it distributes work across multiple cores as well, I think.
The same thread.
I've definitely seen a number of examples just to back it up.
Yeah.
Yeah, it's definitely distributed across.
Yeah. I don't know how to provide evidence, but I know it to be true.
Most of those are distributed across cores, right? Most threads are?
OS threads are, they're put on, when you spawn a thread, it can be put on a different core. The OS can allocate that thread to a different core. And that's how OS threads can be parallel, because they're on different cores. So.
So Phoenix is a web framework. What are practical implications for web frameworks? What are the benefits that you'd see that you wouldn't get out of Rails or Flask or something?
Yeah, so I think if you look at Rails right now, so real-time is a big thing. It's really important. And if you ever tried to write a real-time application in Rails, it's not that easy because it's easy in development, and then you put it in production and it crashes and burns. And I actually had that problem. I had an app that used server-sent events, which is like a long request. And these requests will pile up, and then your app crashes and burns in the queue. So it'll bring your app down. So Action Cable is a new piece of Rails that is responsible for doing these real-time WebSocket connections. And if you look and read about it, you run your Rails app, and then you have a separate OS process running Action Cable. So they're actually taking the same idea that Erlang is, and they're saying okay, this shouldn't be part of our app. If this crashes, it shouldn't bring down your app. So, was that the question? Yeah, so WebSocket connections, long requests. Think of Sidekick. Sidekick runs in another process, so it handles a bunch of work. All these things would just run in your Elixir application. Key value stores, caches, they could all be just part of your application because they are independent, fault-tolerant processes that aren't going to bring down the rest of your app. And that's kind of the reason, the reason we put Sidekick in another process is because if a Sidekick worker crashes, it shouldn't affect the app. It should just fail, and that's fine.
Okay, so I have a couple questions. I'll try to put them in a order that makes sense. So I guess the first is, if shared mutable state is bad, why is it necessary to solve both of those problems? In the sense that you're sharing mutability by having immutable data structures, and you're solving.
Why is shared mutable state necessary to solve which problem?
Okay, so as far as I understand it, Erlang is solving the mutable problem, the mutable half, by implementing immutable data structures, and then solving the sharing part by message passing. So why is it necessary to solve both of those? Because it's only bad if you have both of them in combination. In other words, you could share state all you want if it's not mutable.
Right. That's true, but because they're separate processes, an Erlang process is kind of a misnomer for a thread. Think of it that way. It's like a tiny little thread, but they call it a process because there is no shared mutable state. And the only way those processes can talk to each other, if you have them separate and they don't share any state, you need a way to send the message from here back to there. Shared mutable state would allow you to just update the value over here in your one process, and that would handle the they need to be able to communicate.
Right, but they could communicate with shared immutable state, and it wouldn't be dangerous.
They could communicate, but they couldn't communicate with shared mutable state or shared immutable state because you can't update the value if it's immutable.
What we agree on is that shared mutable state is bad.
Yeah.
But there's definitely ways to communicate with immutable state, right?
Yeah, so I think what you're saying is what Steve Klabnik said, which is there are two ways to solve this problem. You either have no shared state or you have no mutable state, right?
Right, and it seems like Erlang solves both of those problems, or has fixes on both sides of that equation.
Yeah. I'm not sure I have an answer for your question.
It might not be a problem, but that brings me to my second question, which is, if you have big pieces of state and you have you need them in several different Erlang processes, does that mean they're duplicated in memory?
Yes, it does. But because it's an immutable language, it can efficiently copy. So if you read online about performance of Erlang applications versus performance of Go applications. Like Go has immutable data, so you could just boop, replace that data, and it's fine, it's done, and it was fast. So Go is really, if you're doing number crunching, Go is going to be faster, but it's not going to be a better concurrency model. So Erlang doesn't solve the problem of performance through like, fast computations. It solves it through splitting that work out.
Right, but when you implement immutable data structures in a way that's fast, it's done with like trees and structural sharing. So they actually do share the same pointer reference to memory at that point. And so if you have, that's the part, and this is a lack of my understanding about Erlang. Maybe it's doing some of this stuff under the hood, but if you want to copy a gigantic data structure, the fastest way to do it is to take everything that didn't change and point to the same place in memory. So I'm wondering like how it does that. If it's
So I think all of that is handled by the underlying VM rather than Erlang the language. Like Erlang doesn't worry about any of that. Beam handles, the pointer references, the threading, the scheduling. So Erlang never knows about that part of the world. You know what I mean? I don't know if I know what I mean.
It just has access to something and it's fast enough to copy it. It's basically the answer.
I guess, yeah.
So I have some questions about the messaging. So in your example, you were kind of explicitly declaring or explicitly sending messages to process IDs because you knew what those process IDs were.
Right.
But in an application, like what conveniences are there for sort of like automatically discovering where to send the messages?
So there's a global register of process IDs. So you can say, oh, this is my process ID for this process. And if I need to look this up later, I can. And I think supervisors give you that ability too, where you can, if you have a reference to a supervisor, you can look up its child processes. But I think the global register is how you would go about looking up the PID for that process, if that's...
You can register by name.
Right.
And also, and modules and names are kind of the same thing, right? You might give like a module, register one, according to a module, just a module one.
Yeah, you would say like global.where is ping or something like that if you had registered the process.
All right, that makes sense. So what about like if I wanted to send a message to like a group of processes, like if I don't care about like which of the database pool workers gets the message, I just want one of them to get it.
Yeah, so I think like if you look at Phoenix, it has phoenix.repo. And I think I'm sure there's a way to cluster, but I don't really know the answer to that. Yeah, I think maybe that's a function of the supervisor to like send that out, but I don't really know.
There are connection pool libraries that basically give you that abstraction where you just talk to you just talk to one process and it's kind of like a pool and proximate to it.
Yeah.
Gotcha. So I guess my last question would be about what guarantees there are about messaging. Like, is it guaranteed delivery to some target process? Like,
yeah. So if you send a message to a process and that fails, it just restarts and then the message queue is still there, so it just grabs the next one. So there is like guaranteed delivery, I think.
gotcha.
So long as, guaranteed delivery.
There's two ways to send the process. There's a broadcast, which is like a UDP type of like you just send it off. And then there's what they call call. It was call and cast. So call is basically like it requires an acknowledgement.
So there's like something for TCP-esque and UDP-esque. Cool.
A follow-up question. What about process discovery on different machines? Is there a common practice for that?
I think, I'm not really sure about that. I think you like declare a list of distributed servers when you. I know there's some function on Node where you say like node dot I have all these, and then you can say node dot list, and you can get a specific node. But yeah, I don't know about discovery though. I don't know if there's a tool for that or.
And node is the term that they use for a physical machine.
Yeah.
Okay.
I could see this being really great for distributed testing, like if your test suite can run like that because it's distributed across a whole bunch of machines. Is that?
Yeah, well, definitely that, but your test suites are parallel by default in Elixir. So even like your feature tests, all the browser driver libraries are designed to be run in parallel,
Fantastic.
which is really cool. So your tests run very quickly.
Very cool.
So if there's shared immutable state, so let's say you're in the middle of a subroutine or something, and you want to kind of yield to some other process. Is there a way to sort of freeze your state and send it off, or how do you can you spawn a bunch of things that have access to the things that you've declared in your current scope? Like, how does that work? Or does it have to be, is it all explicit message passing? Like anything that goes here, I have to explicitly say, you get this data.
Yes?
I think it's the latter, yeah.
If you want to parallelize, you have to do processes and explicit passing.
Okay.
What have you disliked about Erlang and Elixir?
Just nothing about the language at all. Like I immediately found it to be pretty productive. And similarly to how when I start writing Ruby, I sort of just like thoughts to keyboard. I feel like the same thing sort of happens when you're writing Elixir. And the one thing I haven't liked, and this is something that's going to be fixed, I believe, is the lack of libraries. So there's just not obviously there's more Ruby libraries than there are Elixir libraries, and that's just because it's not as mature. You can lean on Erlang libraries, but there's not for high level concepts like database pooling. There are libraries for that, but there's not libraries for I need a really good form builder. Phoenix has a form builder, but it's not Simple Form or these crazy projects that have been around for a long time for Rails. So.
Thank you.